Welcome. In this video, we'll explore the fascinating world of building management system, or BMS, control logic. At the core of every BMS is its programming, the set of rules and sequences that determine how building systems respond to various inputs and conditions. Whether it's keeping occupants comfortable, optimizing energy use, or ensuring safety, control logic is the brain behind it all. We'll start with the basics and gradually move into advanced programming techniques, giving you a complete overview of how modern buildings are automated and managed. Let's dive in and see how control logic shapes the smart buildings of today and tomorrow. There are several ways to program a BMS, each with its own strengths. Some systems use line-by-line textual code, like Niagara or older platforms. Others rely on function block programming, where you visually drag and drop logic elements. This is common in Schneider EBO or Siemens Desigo. Modern BMS platforms often feature graphical logic builders, making it easier to visualize and manage complex sequences. For advanced analytics or artificial intelligence, scripting languages like Lua, Python, or Java are sometimes used. Understanding these programming types helps you choose the right approach for your building's needs. Let's look at some basic control logic examples. On-off control, also known as binary logic, is the simplest form. For instance, a pump turns on when a tank level drops below 30% and off otherwise. Alarms are triggered if, say, the room temperature exceeds 30 degrees C. Time scheduling is another common logic. Lights can be programmed to turn on from 6 p.m. to 6 a.m. automatically. These straightforward if-then rules form the foundation of BMS programming, ensuring essential building functions operate smoothly and reliably. As we move to intermediate logic, things get a bit more sophisticated. Interlock logic ensures that one system won't run unless another is confirmed ON, like making sure an air handler only operates if chilled water flow is present. Deadband control prevents rapid cycling of equipment, such as turning cooling on above 25 degrees C and off below 22 degrees C. Runtime rotation helps balance wear across pumps or fans by switching active units based on usage. These techniques improve system reliability, efficiency, and longevity. Precise control, advanced logic like PID loops comes into play. PID stands for proportional integral derivative, and it's used to finely adjust systems like valves, dampers, or variable speed drives. The controller compares a set point, say 22 degrees C, to the actual value, and calculates an output to minimize the difference. Most BMS platforms offer built-in PID function blocks, making it easier to implement this sophisticated control. Mastering PID logic is essential for optimizing comfort and energy efficiency in modern buildings. SCADA control takes things further by linking controllers together. For example, a room temperature controller might set the target for a supply air temperature controller, creating a chain of precise adjustments. Sequences of operation, or SOO, detail step-by-step processes, like starting an air handling unit. First, start the supply fan, then open the damper, confirm flow, enable cooling, and finally modulate the valve using PID. These sequences ensure safe, reliable, and efficient operation of complex building systems. Developing effective control logic is a structured process. Start by reviewing equipment specifications and the sequence of operation. Identify all necessary inputs and outputs from your I/O list. Draft your control strategy using flowcharts or pseudocode to visualize the logic. Next, build the logic using function blocks or scripting tools. Always simulate and test your logic with either field devices or virtual points before commissioning. Finally, fine-tune parameters like PID settings and time delays to ensure optimal performance. Variety of platforms support BMS programming, such as Schneider EBO, Tridium Niagara, Siemens Desigo CC, Honeywell Webs, and Johnson Controls Metasize. Each offers unique programming environments, from function blocks to graphical logic and scripting. Best practices include using clear, descriptive point names, adding comments, modularizing complex logic, and setting default values and failsafes. Always provide manual overrides for critical equipment, simulate logic before deployment, and use trend logs for ongoing tuning and verification. For going live, thorough testing and commissioning are crucial. Check every input trigger, test both normal and abnormal conditions, and validate all alarms and safety interlocks. Tune PID loops under real operating conditions and log system performance before and after commissioning. In summary, mastering BMS control logic, from simple on-off rules to advanced PID and scripting, ensures your building systems are reliable, efficient, and intelligent. Structured approach, combined with careful testing and documentation, leads to robust and maintainable automation for any facility.